launched a balloon as a kid, or maybe just seen them randomly flying through the air, when they're filled with helium, they move up pretty quickly. So what happens to them? Where do they go? And why do they tell us not to launch balloons like that anymore? I'll give you a clue. This is what's left of the balloon. No matter what, any balloon that's let go into the atmosphere will eventually end up like this, which is really, really terrible for the environment and is one of the reasons why they tell us not to launch balloons anymore. But why does it explode? What's going on? It didn't touch anything. So what happened? Do you have a bicycle pump like this one laying around your home somewhere? Well, you can do an experiment that demonstrates the same phenomenon as the balloon, but in kind of a reverse order. So take your thumb, put it over the nozzle of the bicycle pump, lift the handle and give it a good push. You'll notice the handle pushes back and even bounces back upward as you try to squeeze whatever air is inside that pump. If you push really fast, it creates a back pressure. So I'm trying to squeeze this air, and the air doesn't like that, and it pushes back. So we're seeing the behavior of a gas here that makes you wonder, what's going on? Why does it push back? So for the next example, it's the same phenomena, but in a slightly different situation, and it's kind of in reverse of what we saw before with the balloon. So we have this is a syringe, and you might have seen one of these either at a doctor's office, or maybe you got one after you got your wisdom teeth taken out. They're pretty common for just they use them to flush out various things or add specific amounts of a fluid or gas to something. In this case, we're going to get 15 cc's or 15 milliliters of gas inside the tube, and there's a little opening right there that allows the gas to get in there. So now we have a tube of gas. And I'm going to take my thumb and I'm going to plug the other end with the end that the gas can go in and out. I'm going to plug that with my thumb, and then I'm going to give this a little push, and watch what happens when I push on that. As soon as I let go, it actually pushes that piston or that syringe plunger back up, and that's doing it all by itself. Okay, so what's going on here? Why would that happen? How is it possible that this is able to just push back up by itself? If I don't have my thumb on there and I push down, that's it. Nothing happens. So there's a lot to be thinking about here. What have I done by taking 15 milliliters or 15 cc's of a gas and squeezing it down to almost 5 before it becomes a little bit hard to move? And then it just comes back up all by itself. So what's going on here? The phenomena we've talked about so far in this video are all real-world examples of something called Boyle's law. And Robert Boyle, this handsome scientist right here, was a major contributor to that law, which describes the relationship between pressure and volume. So in the syringe example we had earlier, I've simplified that into this diagram right here, and we have a volume of gas or an amount of gas trapped inside a tube, and those little yellow dots represent the gas molecules. And because I'm extremely strong, I was able to push down on that plunger and basically squeeze those little yellow gas molecules together, and what you can see is that that amount of space is less. So I decreased the volume by using outside force, but that forces all the yellow dots or molecules to be closer together, and they start bumping into each other and they start bouncing off the sides of the container. So that is what we feel as increased pressure. And because that pressure was so much higher, it actually, as soon as I let go of the piston or the syringe plunger, it pushed that plunger back up because of the high pressure that was going on in there. It didn't like that. It wanted to get back to normal. So that's essentially Boyle's law in a nutshell. And so what you need to do for any of these situations is kind of divide it. We have a before and an after situation. Now, what does that mean? It means before, this is before you change anything or do anything to a system. After means that you've done something. You're going to actually either try to mess with the pressure, you're going to try to mess with the volume in this case. So in this example, we had a pressure before, and we're going to call that pressure number 1. That's before we did anything. And the volume was what it was, and that's volume number 1 before we did anything. And I will say that the pressure was fairly low, and the volume was larger. Okay? So after we push down on that plunger, we actually have a new volume, which is the second volume, V2, and that was much, much lower. Okay? And that caused pressure 2, or the pressure after we did all this, that went way up. Okay, so if you divide all these situations in any kind of gas law into a before and after, you can certainly kind of piece it together and figure it out. Now, Boyle's law says that if we just take these two numbers before we do anything and we multiply them together, so the pressure that we had before and the volume we had before, we get some sort of constant or a number. And he said that because one goes up and the other goes down, afterwards, if you multiply those two numbers together again, you're going to get that same constant. And that's what Boyle's law is all about. So we can apply that to the situation with the balloon as well. So it was a bit different because pressure 1, and by the way, I've switched over, this is a weather balloon, not just a normal balloon. This is something that happens hundreds of times across the country every day, and we launch these to gather atmospheric data about what's going on in terms of temperature and moisture and wind direction and things like that. So there's an instrument package that's attached that's at the bottom of that balloon, and it takes measurements as the balloon rises up into the atmosphere. So down here at the ground, that's how big the balloon is, which is actually a pretty big balloon, but it's at normal, lower or higher atmospheric pressure. So the pressure down here at the ground is actually pretty high compared to when it gets up into the upper parts of the atmosphere where the clouds are and all that. We're going to see that that changes, and I'll talk about that. But the volume of the balloon is what you see. So you can actually measure that and use the volume of a sphere formula to figure that out. That volume, I'm just going to say right now, is fairly low. Here's why. As that balloon rises up through the atmosphere, you're actually leaving the atmosphere. There's less and less air around you, and there's less and less air above. So that takes the pressure off the balloon. So as that balloon gets higher up into the atmosphere, the pressure is actually much, much lower. And so the volume, because there's no pressure pushing the air together inside that balloon, the volume will increase, it'll expand, and that makes the balloon get larger and larger and larger. And actually, I will say, you can see the size of the balloon before in this picture, but by the time it gets to the upper parts of our atmosphere where we're actually taking measurements, that balloon will be about the size of the room you're probably sitting in. So that's a major change in volume, and that gas just tries to expand out because it has much less pressure on it. So that's Boyle's law working again, but kind of in an opposite situation. The other thing that you might notice if you ever get into an airplane, as your airplane, and here's my drawing of an airplane, it's really good. As that airplane goes higher up into the atmosphere, you're going to notice your ears pop, and that's because the pressure outside is decreasing. And so that causes your eardrum to actually kind of want to expand a little bit as the airplane flies up. So that's the volume trying to increase of the gas inside your head. So it kind of pops your ear, and that sometimes can be uncomfortable. But it's the same reason for all of these phenomena is that relationship between pressure and volume, and it's an inverse kind of relationship. So as pressure increases, volume will decrease, and vice versa. We see that a lot in science. Now that we have some background on Boyle's law, let's see if you can figure out a situation that happened when I was teaching chemistry not too long ago. In the following video clip, I'm holding a soda bottle that is sealed off. Inside, there's aluminum foil and some hydrochloric acid. A single replacement reaction begins to take place, which produces excessive amounts of hydrogen gas as a product. What do you think is going to happen? How does Boyle's law explain what's about to occur? Make some predictions. even discuss it with a classmate, and watch what happens.
Drink it.
There it goes. See it?
Yeah. All right, guys, get it away. All right. It worked.
Is it loud?
Oh no, yeah, it's pretty loud.
Holy!
I hope you learned a little bit more about Boyle's Law and how it applies to situations that occur in real life all the time. And if you have any more questions, feel free to reach out to me or your teacher. See you soon, and thanks for watching.